So now we are going to calculate the electron affinity by using an additive coupling scheme. So we have discussed that electron attachment to DNAs is an important problem because they have play a important role in the secondary pathway of radiation damage. What happens is that these electrons are get produced by the action of radiation on the surrounding water, and they get added to the part of the DNA and leads to DNA strand breaking. Of course, this is a model system what we are dealing with, an isolated nucleobase, and we have already seen this system while doing calculation. So, we have the force field parameter already for it. Now, we will take this complex and optimize the neutral and anion, keeping the thymine at XTB level, and also perform frequency calculation. So, up to now whatever optimization we have done in internal coordinates. They are very efficient, get optimized quickly, but problem is that when your size of the active region is very high, like the place you want to optimize, the quasi-neutron optimization in internal coordinate can become very costly. It's heavily memory requiring, it can take a lot of time, and sometimes to generate this internal coordinate actually takes much more time than actually doing an energy or a gradient calculation. So, it can be advantageous to use the LOPT or LOPTAGE feature, which is a LBGFS scheme, takes less memory. It does optimization in Cartesian coordinate although. But although it does optimization in Cartesian coordinate, it's actually takes very less memory. Optimization is slow, but you can at least do the optimization. So, when you are trying to do QMM calculation with a large size of the active space, like active space mean by the region you want to optimize, it's a good idea to check out the LOPT scheme. So, this is how the input file will look like. We are going to do the optimization and XTB based QMMM, although we are calling it QMMM. Remember, XTB is a semi empirical method. So, in principle they are QM, only your Hamiltonian is parameterized to experiments. The other thing is that after we do the optimization, we will do the single point calculation at BP86 MADF to QZ VP using optimized geometry and add the thermochemistry corrections to it and calculate at XTB QMM level. Single point calculation also we are going to do not on the full system, but at the MADF to XBP QZ VP that is what I should have written. And this is how my input file for the optimization will look like. So, let me copy paste it. Let me open a notepad. And this will be first I will optimize the anion. So, I can take the Thymine-water PDB file, I need to make it -1, 2. A few things to notice here. First of all, the input file actually has a bug, and the bug is that I have not ended the QMM region with an end. I have just used the QM atoms to do the end. That is one thing, and this end will be there removed from here. So, let me correct in my slides also. What else? So, my active QM atoms is says 0 to 14. How do I know that? Okay, to do the calculation, I should have went to a new directory, maybe just to avoid confusion. Let me write QMMM. Let me cut this one. And paste it here. Also, I need the PRMS file, so I can go back and copy the Thymine-water.PRMS and Thymine-water.PDB. So, this I will copy and put inside. this one. So now I open it in Mobix term. Before I submit the calculation, let me do one thing. Inside this one, let me calculate inside the QMMM. Let me calculate another directive which is called isolated, because I also want to calculate the isolated neutral anion to see how much its energy changes from isolated from to the solvated in water. Let me go change the view, zoom a little bit. Oh, we have not discussed why we have taken from 0 to 14. So let's open the PDF file with Chemcraft, and then we'll see why we have taken 0 to 14. So here you get the option, you can try to see from here also. It will see you the number, but most easiest way is to show only atoms belong to the chosen subunit. And if you see the number here, it's done from 1 to 15. And if you see the numbering, it goes from 0 to 14. So that means it goes to 1 to 15, because Orca can start the counting from 0. So this is how it should look like. Let's save it again and let us run the calculation. Orca anion. Says that please remove all ASCII characters from this one. Okay, so let me open the output file, that will tell me where is the problem. Line 3. Okay, line 3. Maybe here is a gap, and maybe so wherever this gap is there, generally non-ASCII characters comes there. So let me save it again. No, I want to save the input file as anion.inp. There's again an error. Let's see why is the error. Okay, we have not put the exclamation mark. So we have saved it again. Says that it cannot find the Thymine-water.pdb. Okay. Thymine-water.pdb file is here. So, optimization is going on. Let me open the output file once more with the Vim editor just to show you what happens, what are these steps. So, it says that it has 45 atoms, 15 of them is QM, 30 of them is MM. So, maximum step in the BGFS optimization is 2000. Why I have taken, so up to now whatever optimization we have done in the internal coordinate, we have never written the steps, and because we have always used the default step. But here is the case where we are writing the step because the BGFS uses Cartesian coordinate optimization, so that can be really slow while it goes. So, this is how the things, and the gradient and maximum gradient convergence is 0.99. So, the RMS gradient has to be less than 0.9 in kilojoule per mole per angstrom, and the max gradient has to be 4.9615 kilojoule per mole per angstrom. So, just to show you, it is possible to restart this calculation pretty easily, although we are using XTB. So, we are not going to do the restart here. And remember, we have told that we also want to optimize the isolated thymine. So, let us do that. I take thymine, I save as XYZ, type as character, so this one I can open with Notepad. XTB opt frequency. Again, we will start with optimizing the anion. -1, 2. Is isolated anion. INP although I generally advised against running two jobs at the same time, because here we are using XTB in both and the other job is very small because it is thymine only. So, let me try it. So, now isolated anion is done. I can also do the isolated neutral. neutral dot out. Okay, so these two calculations are done. Isolated neutral and isolated anion. Now you have to do the single point. Remember, the single point has to be done on the optimized geometry, which is calculated using in a much bigger basis set. So I could have done in multiple ways. So the way I will try to do it is I will open the individual files, XYZ files with the Avogadro. You can do it in multiple ways. The way we are going to do is that I will take the isolated anion, then open it with Notepad. I will use the XYZ file format. Isolated anion, and method has to be single point. It will be RIBP86 MA Def2 QZ BP. The single point is MA Def2 QZ BP. Here we are not, of course, we are not doing the QM, only QM, so this should be fine. So let me name it as isolated anion QZ. vp.inp .xyz So the XYZ file name I have given it wrong, maybe.